everybody. So today we come over to the third part of our lecture on special relativity, and having done the postulates of relativity and seen consequences like a length contraction, let's move over to another interesting consequence, that's called a time dilation. Okay, so just to set up the thing a little bit more, let's just have the results which we had in our last lecture. It's mainly on length contraction. So what did you see there? So what we saw there was, if you have a rod, if you have some object at rest in a certain frame, you go and measure its length. Okay, find that the length of this rod, let's say it's L0. Okay, now if you go and measure this in a different frame from which this rod appears to be moving, okay, with an uniform velocity, the length of the moving rod appears to be shortened in the direction of its motion. Okay, of course. So that's the result that we got. So if you see the length of this object, this rod, from S frame, okay, so remember that the rod is at rest in the S prime frame, which is moving with a certain uniform velocity v. Then what's the length that we're going to see in the S frame? It's L0 times the root over of 1 minus v square by c square. So obviously L is less than L0. Okay, so the length of a moving rod or a moving object appears to be shortened as compared to the measured length in its rest frame. Okay, so so having seen something to do with the space coordinates, I mean that's the length contraction. What do we do? I mean, what is it that we have with the time component in special relativity? Does something happen there? Okay, remember in Galilean transformation, of course, time in both these frames, in S and S prime frames, are the same. They're moving with a certain uniform velocity with each other. But is it so in special relativity? If you remember your Lorentz transformations, so there is a space component even in the time equation. Okay, and that in a sense leads to another interesting concept in a consequence in special relativity. It's called time dilation. Okay, so what is it? What's the in long and short of it? It's just moving clocks appear to run slow. Okay, so it's nothing to do with how good the machine inside the clock was. It's the concept of physics here. Okay, or in other words, the time expands for a moving body. Okay, right. So let's take an example, a short one. How do you measure such a thing? How do you get the feel of such a thing, of things like time dilation? Okay, so if you consider a person who is inside a train, and this train is moving with a certain velocity v, okay, with respect to the station, of course, station or stations in this case. Okay, then for the person who is sitting in this train, he matches his own watch. I mean, this he has synchronized his watch with one of the station clocks earlier. Okay, let's say. Then in the next station, when the train passes, he looks at the station clock, and then he'll see that the times in his watch and the station clock will not match. Okay, so that's again what is meant by an example of a time dilation. But let's have a more pictorial example of this concept. Okay, so which will clarify it a little bit more. Say that you have two stations, and then you have synchronized clocks in these two stations. Okay, synchronized in the sense that they give the same the times are synchronized. Okay, so well, I should say that if you have two stations, you need two clocks there. Okay, so so we have our two clocks, one on the left of your screen and one on the right of your screen, as written as station A and station B, and then there are clocks there. Okay, fine. Then what happens? Suppose, let's say, a person moves with a certain velocity in a uniform velocity v, okay, in a train coach, and then he has a watch on his wrist, let's say. So he's talking of a wristwatch, and then he checks his time in this wristwatch, and he adjusts it according to the time in station A, so that he synchronizes his clock with station A. Okay. Now, when he passes station B, okay, what he will observe is that the time, or the whatever time it is in his wristwatch and whatever time it is in station B and then the station clock, they will not match. Okay. So, this is a more pictorial way of saying the thing. Okay. Well, why is it so? Okay. Now, for that we have to be a little bit more quantitative, and so let us consider two events. Okay, I'll explain what these events are. Let's just define what this the space-time coordinates of these events first. Okay, so so we consider two events. We call it event 1 and event 2, seen from two different frames of reference, S and S prime. Okay, and as always, we take the S prime frame that's moving with a certain uniform velocity with respect to S. Okay. If the space-time coordinates of these two events in S frame, okay, that is x1, y1, z1, and t1. So that's measured at t1. And then the second event occurs at position x2, y2, z2, and at time t2. Okay, and correspondingly, these two events occurs in the primed frame with x1 prime, y1 prime, and z1 prime at this position, and at time t1 prime. And then at the second event occurs at the positions x2 prime, y2 prime, and z2 prime, and at time t2 prime. Then what we have, or if you want to be a little bit more specific, now if you wish to define these events in terms of our train example, we take the frame in which the so first we define what our S frame and this S prime frames are. Okay. So, the frame in which the person with his clock is at rest is the S prime frame. Okay. Now, this frame, so it is moving with a certain uniform velocity relative to stations A and B. Okay, and these are fixed in frame S. Okay, so now we've defined what our frames are. So the stations are, so somebody is watching from the station, so that's S frame. Okay, and then and then the person in the train sitting in the train looking at his wristwatch. Okay, so that's the S prime frame. So so when the person passes station A, let's call that as event 1. Okay, so it's got a certain position at certain time. Okay, and similarly, when the person passes station B, let's call that as event 2. Seen from two different frames, of course, the positions are different and the times are also different. Okay. So, so what we have, remember in the S prime frame in which the person with his clock is at rest, the events E1 and E2 has occurred at the same space coordinate, but at different times. Why is that? You see, he is at rest within the within the train carriage, let's say, and then he just looks at his watch at the same position. So his position coordinates are the same. Okay, but then he, from his point of view, he has looked at it at different times, and that's why he gets different times. Okay, and just to keep the mathematics a little bit simpler, we also take moving in the common x and x prime direction, so that the y primes are also y's and z's are also the same here. But in terms of coordinates, in the S prime frame, we have x1 prime is equal to x2 prime, and then y2 prime is equal to y1 prime, and z2 prime equal to z2 prime. Z1 prime is equal to z2 prime. That's it. But the times are different. Okay. So what are these times, quote unquote, times in S frame? That's seen from the station. Okay. So from the unprimed frame, if we call this the time T1. Okay. So we just have the Lorentz contraction equations, or Lorentz transformation equations to be more precise here. So so T1, that is T1 prime plus V x prime by c square divided by root over of 1 minus v square by c square, and T2 is T2 prime plus v x2 by c square into root over of 1 minus v square by c square. Okay. So the time interval between these two events, according to the observer in S. Okay. So according to the measurement made in S frame, so that's delta t, let's say. So what's delta t now? So delta t is just T2 minus T1, okay, and that is T2 prime minus T1 prime plus v by c square into x2 minus x1 prime divided by the usual denominator root over 1 minus v square by c square. Okay. Now, what's the time interval according? So that's the time interval of these two events according to the observer in S frame. Okay. But in the S prime frame, remember, the positions of these two events were the same. Okay. So we have x2 prime and x1 prime are the same. So x2 prime minus x1 prime is 0. Okay. So that will give us what? That will give us that this delta t is delta t prime. So we have defined delta t prime as the time difference as measured by the observer in the S prime frame. Remember, the S prime frame is the one in which the person sitting in this train carriage is looking at his watch. Okay. So what do we get? So what we get is delta t prime is delta t into root over of 1 minus v square by c square. Okay. So just you get a feeling that you immediately see that delta t prime is actually less than this delta t here. Okay. Now, what does it mean physically? It means that the time interval measured by the moving clock relative to S will be smaller than the time interval measured by the clock stationary in S. Okay. So in other words, what we have is confirmation of the statement with which we started with, that moving clocks run slower. However, I should remind you that if the velocity is much less than the speed of light, then you will immediately see that these two time intervals are the same. Okay. So they are approximately the same. So the next time you come from, let's say, Delhi to Roorkee, and then you look at the station clocks. Supposedly, I mean, you're moving with a uniform velocity and all these things with respect to the station in all cases. You shouldn't, well, you shouldn't and you wouldn't see this this time dilation. Okay. Okay. So having seen this thing, let's have a look at what proper time is. Okay. So what's a proper frame? What's a proper frame of reference? So a reference frame in which body is at rest is called its proper frame. We know that, and we've also measured. We know what a proper length is. So the length of the body measured in this proper frame is called its proper length. So the time measured by a clock at rest in the proper frame is the proper time. Okay. So just like the proper length is the proper time invariant, well, I think it is, but let's just have a look at it once again. Okay. So so the time interval, so what's a proper time interval, to be more precise? So it's the time interval measured between two events by a single clock at rest at the same place is the proper time interval between two events. We just had a example of a person sitting in a train looking at his watch at two different stations. So that's an example of, you know, his position is not changing according to him in he's sitting in the same place in the carriage, so his position is not changing, and then he looks at his own watch, so that's a single clock, and he's sitting at rest in the train, so according to him he is measuring the proper time, okay, by a single clock. However, I mean, at the same time interval, you know, if you're going to measure it from another frame having a relative velocity with respect to the proper frame, so you need two clocks at different places. So that's exactly what we had. We had two stations and two clocks, and then they had to be synchronized in the beginning. Well, in a sense, this time sometimes is also, this kind of time is also, time interval rather, is also called non-proper. Okay. So so if the velocity of the second frame be of another frame be v relative to the proper frame with proper time interval delta tau between these events, then the non-proper time interval delta t measured from the second frame, of course, by subtracting the time measured from two different clocks, will be delta tau divided by root over of 1 minus v square by c square. Okay. And so what's this delta tau? That's the proper time. So it's delta t into root over of 1 minus v square by c square. Okay. Now, if in another frame in which it's moving with a velocity v prime with respect to the proper frame, if the time interval measured between the same two events is delta t prime, then obviously delta t prime is again delta tau divided by root over now v prime squared by v squared. So you immediately see that if we just write out the delta tau here, the delta tau is nothing but delta t into root over of 1 minus v square by c square. That's the time corresponding to this measured in the frame, the time interval measured in the frame, it's moving with a certain velocity v. Then t prime, this time interval measured in the frame in which it's moving with a certain speed v prime. So that's equal to delta tau. Okay. And so delta tau is invariant quantity. Okay. So the proper time, just like the proper length, is an invariant quantity. Okay, so let's look at an example. Okay, or let's look at some examples here on these consequences of time dilation, proper time, and see what else we can do from here. Okay, let's take a simple but interesting example. So you know a muon, that's a subatomic particle. Okay, and a muon is observed to move approximately something like 800 meters on an average during its lifetime in a laboratory. Okay. So, if one looks up the mean lifetime of a muon from one of these particle physics books or these data tables, you see that it is something like 2 into 10 power minus 6 seconds. Okay. So, if we just go and write the velocity as the distance covered and then its mean lifetime, so that is 800 meters by 2 into 10 power minus 6 seconds, we end up with 4 into 10 to the power 8 meters per second. Okay. And this is much bigger than the speed of light. Okay. Now, this is heresy in special relativity, and what do? I mean, obviously we haven't considered something. So, what's that? Well, one needs to consider that what is given as mean lifetime of this muon is actually its proper lifetime. Okay. So, when you are measuring the length in the laboratory, okay, so you need to divide this by the this quote unquote improper lifetime. So, the measurement of the time and the measurement of the distance this muon has traveled should be done in the same frame, that is it. Okay. So, this quote unquote improper lifetime of this muon as measured in a frame moving with this velocity v with respect to this proper frame. So, what is that? So, if we remember just a few slides back, we talked of the proper time interval, that is divided by root over 1 minus v square by c square. So, the proper time here is 2 into 10 power minus 6 seconds. So, we divide that by root over 1 minus v square by c squared. Okay. And that is what we get. The speed of the muon is now 800 meters divided by delta t, that is this improper lifetime. And if you put in this expression which we obtained earlier, you will land up with the speed of this muon to be a 4/5 of the speed of light. So, this is still less than the speed of light. Okay. And it does not you know, it is not more than speed of light as we had done, as we had seen it would be if you do it in a wrong sense, of course. Okay. So, let me now move over to another interesting concept. It is the relativity of simultaneity. Okay. So, and then I shall later on talk of things called earlier, the concepts of earlier and later. Okay. So, the concepts like if you if a certain event is following a sequence, I mean some event has occurred earlier and then later, and then does it appear to be in the same sequence in some other frame or not. Okay. But before that we do a little a more basic thing. It is called this relativity of simultaneity. So, so what is it that we are going to say here? What we are saying is that two events are said to be simultaneous if they occur at the same instant of time. Of course, I mean that's the basic definition of what you would see for a simultaneous event. Okay. But the question is, if these events are to be simultaneous in one inertial frame, So, is it going to be simultaneous in another frame of reference, which is, so when you talk of inertial frames, so the frames here are moving with uniform velocity with respect to each other. Okay. So, if it is simultaneous in one frame, is it going to be simultaneous in another frame? Okay. So, for that, I think it will be good if we see it in a more pictorial fashion here. So, we talk of event 1. Okay. So, we say event 1. So, now it's occurred at a certain position. So, the x1, y1, z1 say at certain time in S frame, let us say. Okay. And then the same event is seen to be at positions at position x1 prime, y1 prime, z1 prime, and then the time measured is t prime. Okay. So, that is the event seen from the frames S and S prime. So, remember S prime is also moving with a certain uniform velocity with respect to the S frame. Okay. Now, if we talk of another event, okay, seen by the observer in S and S prime frame. So, it is occurred at a different position and time altogether again. So, okay. So, what's the relation between this between these time components? So, we know it. We know it's t1 prime, that's equal to t1 minus v x1 by c squared divided by root over 1 minus v squared by c squared. Okay. So, and same thing for the second measured time in frame S prime. So, that is t2 prime is just t2 minus minus v x2 by c square divided by 1 minus v square by c square. Remember, this unprimed things are for the S frame, and then this prime things are for the S prime frame. Okay. So, what is the difference between these two times? Okay. As seen, well, the difference between these two primes is obvious. So, it is t2 prime minus t1 prime. So, we find that is the same as t2 minus t1. So, things on the right hand side are the coordinates, the time that we have in the S frame. Okay. So, that is t2 minus t1 minus of v of x2 minus x1 by c square and divided by root over of 1 minus v square by c square. Okay. So, if these events are simultaneous in S frame, okay, then of course, it's occurred at the same time. So, we take t1 is equal to t2. Okay. So, that would mean that we have from this equation of difference of times in the prime frame. So, we have on the right hand side we have taken out t1 minus t2. Okay. However, so the position, so that is x1 minus x2. So, that, well, it is not 0. Why? Because if it is 0, so you would not be able to distinguish between these events. Okay. So, so that is not 0. Okay. So, that would mean that the difference of measured times of these two events in the prime frame is not 0, because none of the quantities here are 0. You can see here. Okay. So, what do you get? So, what we get is the measured times in the S prime frame need not be the same, even if the times are the same in the measured times are the same in the S frame. Okay. So, in other words, to be more precise, what we have is that the events E1 and E2, okay, although they may be simultaneous in one frame of reference, they need not be simultaneous in another inertial frame. Okay. Okay. So, we come then to Another interesting concept, it's the this thing called the sequence of events. Okay, the concept of the earlier and later. As we said, I mean, what we saw is that if something is happening, earlier in a certain frame, and then another event is happening later in a certain frame, is this order of events preserved? Okay, so why do we say that? Because we've just seen that this simultaneity itself is a relative concept here. So it depends on it need not be a something which is simultaneous in one frame of reference need not be simultaneous in another frame of reference. So will this occur here too? I mean, in this sequence of events. So we consider two events E1 and E2 again, and we see these events from two different frames S and S prime. Okay, so this S prime frame, it's moving with a certain uniform velocity with respect to S. Okay, so we have written down what the space time coordinates of these two events are in S frame and the S prime frame. Okay. So the question that we now ask ourselves is that if these events occur in a certain sequence in one frame, so can it occur in the reverse sequence in another frame? So for that, we again have to look at the difference of times as measured in the S and the S prime frames. Okay, so what's the difference of time measured in the S prime frame? So that's T2 minus T1. That's the time measured in the difference of time measured in the S frame minus of the velocity v into x2 minus x1. That's those are the positions as measured in the S frame by c square, and then the usual factor root over of 1 minus v square in the denominator. Okay. Now, if let us say event 2 has the second event has occurred later than event 1 in frame S. So, obviously, T2 minus T1 is positive. Okay. Now, that means that for the reverse to happen in S frame, okay, what we have? We have T2 minus T1 was positive in S frame, but T2 prime minus T1 prime. So, that is not positive. Okay. So, in that case, what it means is that we have the thing in the numerator. So, that is T2 minus T1 minus of V into x2 minus x1 divided by c square. So, that has to be negative. Okay, that is obvious. The denominator here is positive. Okay. So, now if that is so, we would require x2 minus x1 divided by T2 minus T1 to be greater than c square by v. Okay. Now, if these events are causally connected, that is in a sense that event E2 is happening as a consequence of event 1 happening. Okay. It is more like you in a cricket field, and then think of your favorite cricketer, and then what he does is he autographs a ball and it throws it at you. Okay, and then so you catch the ball. So he the cricketer, your favorite cricketer, autographing a ball, and then that's called an event 1, and then you catching the throw that he throws, that at event 2. So this has to be done at a certain so certain the message has to be passed at a certain speed here. Okay. So you catching an autograph ball is in a sense dependent on your cricketer signing the ball. Okay. So, unless the cricketer signs the ball and throws it to you, you cannot catch the ball. Okay. So, in a sense, some message has been passed in this case, example of two events which are causally connected. Okay. So, in a sense what we have is that some message which is originating from the first event reaches the second, the place, the position of the second event, traveling with some speed, let us say some speed u. Okay. Then the minimum speed that this u should have is actually x2 minus x1 divided by t2 minus t1, difference of these positions and the difference of this measured time. That is the minimum thing, that value that you should have. Okay. U, that is the alphabet u, I mean. Now, what does it mean? Now, this u in this case would have c square, would be more than c square by v. Okay. Why? Because x2 minus x1 divided by t2 minus t1, that is more than c square by v. So, that is the condition one has to satisfy, remember, if the sequence of event is reversed in another frame and the events are causally connected. Okay. But then we will end up with a problem. The problem is that v here is less than c, okay, or at most it is c. So, at most it is c, but so you cannot go more than the speed of light. But then what about u, the alphabet u, that is the speed u, you see that it is more than c. Okay. So, this again is not allowed. So, because why? As I said again, because v is the speed, S prime frame is moving uniformly with respect to a frame S. Okay. So, in a sense it would mean that the message between the events E1 and E2 is traveling with a speed greater than the speed of light. So, this is not allowed. Okay. So, this condition is not fulfilled, this condition is the wrong condition. Okay. Now, since it is not possible to fulfill this condition, if the events E1 and E2 are causally connected, then it means that the concept of earlier and later between events will be preserved in all inertial frames. Okay. So, that is the point here. So, if the events are causally connected, then it is going to be preserved, but if the events are not causally connected, okay, so the second event, let us say, is happening independent of whether event 1 occurs or not. Okay. In that case, the opposite can be true. Okay. So, that is the case when they are not causally connected. Okay. So, what we saw is that all these things called the simultaneity or the relativity of simultaneity tells us that if two events are simultaneous in a certain inertial frame, so it need not be simultaneous in another inertial frame. Okay. But the concepts of earlier and later, so that is preserved if the events that we are talking of, they are causally connected. Okay. So, as usual, let us have a few examples to clarify our concepts. Okay. So, let us take two events here, E1 and E2, and in S frame, and we give the position coordinates of these events here in the S frame, and also write down what is the times here. So, here let us say E1 is happening at position x1 is x0, and then the y and z's are 0 here. So, okay, and the x2 is happening at a position 2 x0, and then the time t1, that is x0 by c. So, c being the speed of light, and t2 is x0 by 2c. Okay. Now, if this event is simultaneous. So, see that in S frame this event is not simultaneous, it is happening at different times. Okay. But if this event is simultaneous in another frame, so which is moving with a certain velocity v, let us say, along the common x prime axis, okay, relative to the S frame, what is this velocity and what is the time that what is the simultaneous time that is being measured in S prime frame. Okay. So, how do you go about doing these things? So, let us look at the time intervals as seen from the S frame and the S prime frame. So, since the events are simultaneous in the S prime frame, so T2 minus T1, so that is 0. So, if you look at the second step or the second equation, so on this numerator you put in the times that we had for the event in for the events rather that we had in the S frame, and then also the difference of their positions, and divide it by the root over of v square minus 1 minus v square by c square, v being the velocity with which S prime frame is moving with respect to the S frame. So, we immediately get what we get the left hand side to be 0, of course, and we can immediately find what v is, and we see that v is actually minus c by 2. Okay. So, how do you find the time in the prime frame? Remember, in the prime frame the events are simultaneous. So, so T1 prime, that is nothing but T1 minus Vx by c squared, okay, divided by root over 1 minus v square by c square. And then what you are going to do is they are going to substitute T1 by the measured time, for a certain position. So, if x is x0, we look this problem that the this was measured at time T1 is equal to x0 by c, okay, and we know the velocity now with which this prime frame is moving. So, that is minus c by 2. So, immediately get what this time is in the prime frame of reference. So, T1 prime is root 3 x0 by c. Okay. So, let us go to another problem. Okay. Well, let us look at this problem first. Okay. So, in a certain inertial frame, let us say, so we have two events which occur at the same place, and they are separated by a time interval of 4 seconds. Okay. Now, in another inertial frame, the question is what is the spatial separation, what is the separation in the space coordinates here between these two coordinates if these are separated by a time interval of 6 seconds. Okay. So, that is what we do. We first try to find what is the velocity with which these frames are moving with respect to each other. Okay. So, call the prime frame, that is the so the frame in which the time separation between these two events are 6 seconds. So, that is the prime frame, say it call it like that. So, what is the corresponding portion of this time difference in the S frame? How do you do it? So, it is T1 minus T2, or it is T2 minus T1 rather, minus V x2 minus x1 divided by c square, root over of 1 minus v square by c squared. Okay. So, here we have so you put, instead of T2 minus T1, you put that to be 6, and T2 minus T1 you put that to be 4, and you find what V is, and this V in this particular case would be root over of 5 by 3 into the speed of light. Okay. Now, having found that it's very easy to find what the spatial separation is. So, we just find what the spatial separation is. So, that is x2 prime minus x1 prime, that is x2 minus x1 minus of v into t2 minus t1 into root over of 1 minus v square by c square. And we know the spatial separations in the S frame, that is 0, it's happened at the same place. So, what is the spatial separation in the prime frame? So, that actually is you put in the proper times here. So, I mean the proper times, not in the sense of proper time, proper length. I mean you put in the right times here. So, that is t2 minus t1, and you get the difference to be minus 2 into root over of 5 c. Okay. So, the proper length, the proper separation is the modulus of this, of course. So, that is twice of root over of 5 c. Okay. So, we have seen so far it's another consequence of time dilation. We have talked of we have talked how or why moving clocks run slow. Things are it's we derived it from we derived this consequence from the Lorentz transformations. Then we talked of the relativity of simultaneity. So, in which we showed that two events which are simultaneous in an inertial frame need not be simultaneous in another frame. Okay. And then in the third part, we saw that the sequence of events they are preserved in all inertial frames if the events are if these events are causally connected. Okay. So, in the next lecture, what you are going to see is talk of Doppler effect in light, and see what next we can do from there. Okay. Doppler effect, I think we are a bit familiar with Doppler effect in sound, where if you have a source moving, or you're standing you're standing at a distance, and then from a distance a train is coming at you. Okay. And the train is blowing its horn or giving a whistle. Then you see that as the train moves towards you, the frequency that changes. Okay. So, that is the Doppler effect. So, the source is moving here. So, or if the source is at rest and the observer is moving, the observed frequency of sound is also different. So, we are going to look at whether Doppler effect is there in light or not. Well, that is a thing for the next lecture. Thank you very much.